All right, welcome. Yet another lecture on machine learning. Please put away your laptops, close your laptops, iPads, game stations, PlayStations, I mean. Okay, good. We've been talking about, quick logistics. Sorry, I promised to ruin your weekend with homework 3, project 3. It has not happened yet. We are actually we are test driving it very, very carefully before we roll it out, and we ran into some problems on the auto grading thing. So I think it's all resolved right now. We are testing it one more time, and hopefully we can ship it out tonight. Also, one good thing that happened is we were in contact with Vocarium, and actually Vocarium is now on Piazza. So they actually have now one of the people from Vocarium, from that company, is now one of the Piazza TAs. So if you actually post a problem with Vocarium, he's actually very responsive, and they're very, very interested in making this work for us. Okay, good. Any other questions about logistics? All right. So we've been talking about naive Bayes. Right? A naive Bayes is a generative algorithm. So what you do is, in some sense, you have your data. Let me draw a little example here. And let's say you have positive and negative points. So here are my positive points. And here are my negative points. In this case, it's very easily, nicely separated. And what naive Bayes does, it actually estimates the distribution of this data. So what we're estimating is P of x given y, right? So basically what it says, okay, well, only the points that have label 1, what is the distribution of these data points? And so, you could basically imagine there's kind of a, some distribution. I hope people understand this painting here. This is kind of like a hill, right, of probability that you could estimate in this space. But turns out that's really, really hard because the space is high dimensional. So what naive Bayes does is it says, we make a very simple model assumption. We assume these different dimensions are independent. So in some sense, what are you doing? You just take this data, you project it onto each axis, right? So we say here, now you have the points like this. And now you model this here, okay? And this is easy to model, right? Because it's a one-dimensional problem. Then you do the same thing with the second dimension, right? So you project the data onto here. And now you model this stuff, right? And you say the distribution here is basically, if you combine these two independent product of these two independent distributions. Okay, so that's the idea behind naive Bayes. And so when we do it, when we have data, there's basically 2 steps. The first step is we take the data, we look at each dimension individually and model this distribution. And then once we have it, then we basically have a term for this expression here, which is a product of all the individual distributions for each feature. And then we can do prediction with the Bayes formula. Okay, so then we just fall back onto the Bayes optimal classifier. One thing that's important about naive Bayes is that basically there's a 2-step approach where you first model the distribution and then you make your prediction, right? So when you make your prediction, the data is no longer important, right? You just try to, first you model the data with the distribution, but then you only look at the distribution and predict P of y given x using the Bayes formula. Okay? So if your modeling is bad, then actually your classifier is going to be bad. The nice thing is it's very, very fast most of the cases. Especially, last time we talked about how to, we started going over some examples, how you do this. So one is when you have categorical data, your features are categorical. Then we just have a binomial distribution. We basically just do counting. We just count how many times have we seen this particular feature for label 1 and how many times have we seen label 1 overall, and the ratio is basically the probability of a feature given that label. Okay, so that was what we did last time. We basically, how do we estimate P of x alpha given y, right? It was basically just, the ratio of how many times do we see this particular feature out of all the samples that we had. Any questions at this point? Just, this is just a high-level overview one more time to make sure you're reminded of the big picture of naive Bayes. All right, so what I want to do today is I want to go through more examples, the multinomial and then the continuous features. And then I want to talk about, well, actually, once we have these two distributions, we then have a classifier based on these distributions. And the way it works is, we have a distribution here. For the negative points, we have a distribution for the positive points. And then we take some test point, and we say, what's more likely? Right? Is it more likely that this point was drawn from this distribution, or more likely that it was drawn from this distribution? Right? That's basically how the classifier works. And somewhere in between is a decision boundary, where you say, at this point, it becomes more likely that it's drawn from this distribution. And here, it's more likely that it's drawn from this distribution. And what does that decision boundary look like? So the second part of the lecture, I will talk about this. And actually, I can give you the punchline already. It actually turns out it's a linear classifier. Yeah.
So what about? Sure, I dropped the question.
Okay, sure. All right, no question. Okay, no question. All right, good. So we're estimating this. By the way, one thing we're also estimating P of y. Right? So P of y is usually very easy to estimate. You just count how often do you see each label. Right? It's just a fraction of seeing that label across all data points. All right, any more questions? Yeah?
So I asked you this before. You said we use the orthogonal components of the...
If you use the what? The
orthogonal components?
Orthogonal components? So you mean the axes, like each dimension you mean? Or is that? I see. So what you're saying is the following. What if I change the coordinate system? Right? What if I actually now say my coordinate system looks like this? Right? Now I do PCA. So now I do naive Bayes. Right? And so you now changed your assumption. Right? You're basically saying that after this transformation of this different coordinate system, now all the different dimensions are independent. Right? Conditionally independent. That may or may not be true. Right? Usually it's not true, but it may work. Right? Typically, the scenarios where you'd use naive Bayes is with text documents, for example. There it doesn't really make sense to have a transformation, right? Because the data is very high dimensional, right? And it'll be very expensive. And in some sense, the features, of each dimension corresponds to a word is a pretty good representation of your data. But yes, you could do it. Yeah?
Remember my question. For regression, does this also work?
Naive Bayes for regression. That I don't really know how to do that. No. Yeah. Okay, any more questions? Yeah, over there.
What if you ended up estimating some kind of crazy distribution for all the different dimensions? How would it still be a linear classifier?
Oh, it doesn't. Oh, well, be patient. Be patient. We will get to this in a little bit. Yes, it doesn't always have to be a linear classifier. You got me. So it's not always. It's in several common cases. It's a linear classifier. Yeah. Okay. Any more questions? All right. So I think where we left off last time was the multinomial distribution. I think I just started describing it, right? But I didn't get into the equation. Is that correct? Yeah. Okay. People are nodding. So it really, with these generative models, it really helps to have a model that you have in mind how the data is generated, right? So that's in some sense why it's called generative model, right? We're estimating this here, right? So think of it as some kind of process that takes the label as input and then generates an X, right? And so think of X's now as emails, right? So then in the multinomial case, multinomial, here we basically say the way we write an email, the way we populate an input vector is by adding on to the different dimensions. So we have, so what does that mean? So each X basically is a very large vector, and each dimension here is a count of how many times we have observed that feature in our data instance. Okay, so I explained this last time. So in words, typically we have some description of the English language. So you basically have all the words in the English language, and this can be millions, right? So if you work for a spam filter company, as like Google or Yahoo or something, right, you would actually use all the languages in the world, right? So turns out actually what you usually do is you hash them, but eventually we basically have millions and millions of these buckets, and down here is maybe zebra, or who knows, right? And you count how many times do you have a certain word in the email. So for example, 5 times we saw the, 3 times we saw a, and we saw actually twice, right? Because I'm writing about ants, right? Who knows? And once about zebra, I saw most of these words, however, I will have never seen, right? Because most emails do not contain most words. And the process basically is, the way you have to think about it is you start with an empty email, which is really how you write your emails, right? You start with an empty document, and then you add one word after another, right? So you increase one of these. And what you do is you roll a die, right? You roll a die and say, all right, what word came up? The word pumpkin came up, right? And then you increase your count of pumpkin by 1. Okay, and then comes the next word, right? And now you roll it again, and it's like, oh, unicycle, great, right? So you increase your counter of unicycle, etc. Right? So and you do this until you have m words, and then your email is finished. So that's the process. This is the generative process, how we assume our data is sampled, right? Now again, this is obviously not how we write emails, but it's a process that gives you something that looks like an email, right? And it turns out if you make that assumption, ultimately classifiers work fairly well, actually. Right? So it's an approximation, of course. Okay, so the question is, any questions at this point? So what we want to estimate, in order to estimate this, we basically have to estimate this die, right, that we are rolling. That basically says, what's the probability that we're picking this particular word? Okay, that's basically says for, given the label y, what's the probability that I pick word j? Okay, and that obviously has to sum up to 1, because it's a probability distribution. And we call, I think I already talked about this last time, right? So, okay, let me just write this down one more time. So we have the probability of a particular email x, given that I have m words, and I'm from the class C, so that's either spam or not spam, is the following. It's just the product of alphas 1 to m. So I roll my die m times, and so this here is, see here, alpha goes over the dimensions. This is basically word alpha, right? This here, the theta basically is the probability of ending up with word alpha. This is some value between 0 and 1. And how many times did I roll that? Exact alpha, x alpha times, right? So that's basically the probability. And then I have to make sure that actually the ordering doesn't matter, right? So in this case, actually, I'm just looking at the words. I'm not looking at the sequence of the words. So if you write, the and the zebra, or zebra and the, or whatever, it's the same thing, right? It's in our representation. This is why it's called bag of words, right? Because the word order is thrown out. It doesn't matter anymore. And it turns out to recognize spam from not spam, the word order usually is not important. So just word frequency statistics is enough. So then we also multiply by this whole thing by m factorial over x1 factorial, d factorial. So this here just gets rid of the order. It's not very important. It's just a constant. Okay, any questions about this? Raise your hand if this makes sense. Okay, some people seem confused. Okay, let me explain it one more time. So I basically assume that my data is drawn from a distribution, p of x out y, that has a parameter vector theta. And that parameter vector theta, I have one for each class. Right? For each class, I have this is basically my die. This basically says, what's the probability? Theta alpha c says that if I have let's do this, theta alpha spam, right, is the probability that if I want to write a spam email, that I randomly draw the word alpha. And I roll that die m times, and I always look which word comes up, and I populate this vector this way, and at the end I have a vector with word counts, and that's my email. And what we now want to do is say, okay, well, if you make this assumption, now given the emails that we have in our spam inbox and in your not spam inboxes, I can now estimate this die. I can basically say, what's the, if you assume this is actually the process how emails are generated, now I can look at the data and say, what's the most likely die that would have generated the data that I'm seeing? And that's exactly maximum likelihood estimate. I can do this. So I can basically say, okay, now we want to estimate theta alpha c. So one more time, I want to know what's my estimate of what's the probability that I will see word alpha given that I have class C. So this is given that it's spam or not spam. And how do I do this? Well, it's actually quite intuitive. I basically say how many times did I see word alpha in my spam emails. Right? So that's basically the fraction. So I say I sum over all my data. I say the number of times. First thing is I must have this class, right? All the, let's say, spam emails. I sum over all my spam emails, and I count how many times. This here is how many times I see that word alpha in those spam emails, and I divide it by the total. See, y equals c, and this here. Can anyone tell me what this here is? All right, I give you 1 minute. Discuss it with your neighbor. Figure out what does this mean, and describe to me this fraction. All right, who thinks he or she has figured it out? Who can describe it? What does this mean? Actually, I just realized this should be an I. Maybe that threw people off. Okay, there should be an I here, right? I beta. Okay. Okay. Now that I correct the notation, yes? Actually, that's not quite correct. This basically go over xi, yeah?
How many words is in the xi of I spam?
That's right, that's right. So basically it's the, here you sum over all emails from 1 to n. Here you say, this here is 1 if it's spam, and if it's otherwise it's 0. So you only look at the ones that are spams. You could also just say sum over all the spam emails. And this basically says, go over all the dimensions and sum up the count of how many words there are. Right? So basically go through every single word and say, just, have a cumulative accumulator that basically just says, just adds up how many words you have in total. You know that's actually m, right? And we assume that each email has m for simplification. But this also generalizes, if emails have different lengths. So then actually you need this term here. All right, and so here what we do is we sum over all emails and we say, again, we only sum over the emails that are spam. And then we say, how many times do we see word alpha, right? So basically what we're saying is we'll say, well, in total, right, you go through the entire spam box, right? And you say the word Nigeria, right, which is like a common word for spam. I've seen that 55 times. That's up here. I go through all my emails. And for each email, I count how many times have I seen that word. So 55 times. And then I go through all my spam box and say, how many words have I seen in total, right? Maybe 10,000, right? So then the probability of seeing Nigeria in a spam email is 55 over 10,000. Okay? So that's basically the estimate. So in other words, if you would now go through your spam box and pick a word randomly from all your spam emails, right? That's exactly the probability that it's word alpha. Okay, does that make sense? Can you raise your hand if that makes sense? Okay. And so if you want to do map smoothing, you basically have to hallucinate some words. And the way it works in this case is that you actually have to sum up, if you're going to do +1 smoothing, for example, and you have +1 here, and then here we actually have to sum plus d. Can anyone tell me why we have to add d here? Anyone except him? What's your name?
My name is Arthur.
Arthur. Okay, not Arthur. Anyone else? Next time I pick you again. Yeah. That's right. That's right. Exactly. Right. So earlier on we had each feature where we said we assume that in this dimension we see each value once. Right. Now actually the dimensions are counters. Right. So what we are doing is we assume we see each word at least once. Right? So we add a 1 here, but down here we have to divide by, add a d. D is the number of words in the dictionary. Okay? And that's typically what you use. Right? Because if you don't do this, someone puts in some really rare word, or someone misspells a word that you've never seen before, and then suddenly you get a probability of 0, because you say, well, the probability that this word appears in spam is 0 because I've never seen it before. Right? But that's actually not what you want. Right? So these rare words, usually one way of dealing with this is you just assume that you've seen each one at least once in either spam or in not spam. Any questions? Yeah?
So, this is basically throwing out every single email that is not spam and not taking any information from it, right?
Well, this is just when you estimate what's the probability that I see word alpha given that I have spam.
Okay.
Then you do the same thing for HAMP, which is not spam.
Okay.
Yeah? Good question. So you run this twice, right? So you may now see why naive Bayes is so popular in spam filtering. Because what do? When a new email comes in, all you do is you go through the different words of that email and increase the counters, right? So for each word, basically, you store this counter and you score this counter, and you just increase both of them, right? And then you're done. So learning is really, really fast. You don't have to retrain anything, you have to run anything, etc. Right? So that's why most of your software probably uses the naive Bayes classifier. Yeah? Sorry, here, yeah.
What is our misspell the word to find your vocabulary?
Okay, good question. So he's saying, what if I misspell a word, right? So there's these people, I don't know if you remember this, there was a time when Viagra spam was really, really big, and then people started misspelling it because exactly this reason. People use naive Bayes classifiers, and so then the probability of Viagra, given that it's spam, was really high, and it was really rare in not spam, so it was a very good feature, right? And the spam didn't get through anymore. And then what people did is they wrote they wrote it like a 1, right? They wrote it this way, right? You don't actually want to write Viagra on the blackboard. But and so then actually, humans still recognized what the word meant, but actually, it didn't index anymore because it wasn't actually a known word, so people just threw it out, right? And so, well, one trick, actually, what we actually did, so when I worked on this, we just write a hashing function. So actually what we do is we actually don't have a mapping from words to dimensions, like not a dictionary lookup. What we do instead is we actually have a hashing function that takes this word, the word as input, like y, whatever, and that outputs some number between 0 and d. And if it's a hashing function, so anything you stick in there gets mapped to some dimension. So if they make up new words, then basically next time you retrain, you will actually have populated that word. So that's the trick. That's also how you get around many languages. And also people kind of suddenly write LOL or something. That was a new thing that came out 10 years ago. And so you have to kind of, these new abbreviations that kids come up with, you can just track them this way. Yeah? All right, okay, you're on to me. So in the case of collisions, you just say, well, come on. It doesn't matter all that much. So he's basically saying, what if I have two words, right? Like what if I have, let's say here you have a really, really unfortunate coincidence, right? Like the name of your mother-in-law, right? Matches Viagra, right? Like it goes in the same thing, right? So now all these emails go in the spam filter, right? So there's actually two tricks around it. So one thing is, so what we actually really did is we actually just hashed it twice with two different hash functions. And so they're approximately uniform. The probability of getting the same collision twice is basically 0. So then actually, if one collides, then actually the other one doesn't. And then you're still fine. But it's a very good question. Yes? OK, any other questions? Yeah?
If this is being implemented in software and you mark a lot of emails as spam, would there be some kind of scaling over time so that you wouldn't, overflow after having...
Oh, these counters? So the question is like, if these counters get too large, do you run into overflow problems? So the question is like, if I just, send you an email just with, a million times Viagra in it, right? Then I hope that the counter gets so large that it rolls over and goes to 0, right? And then I've got you, right? I know you can try it. My assumption would be that you use enough bits for these counters that you should be fine. You have to really attack. I mean, I don't know. It's a pretty obnoxious attack. It's a good question, though. It's a good question. OK, any other questions? All right. So this is the case. This is actually the most common case for text classification. So spam filters actually usually use multinomial classifiers. Also for project 3, which is coming out tonight, you actually have to implement a naive-based classifier, and so that would be one option. And I can show you in a minute what it looks like. Yeah? Sorry, what is the? Oh, here, this constant here, just make sure that you don't incorporate the order of your email. Right? So this basically says, you go through every single word in order and say, what's the probability that I got that order that many times, right? But if you would now shuffle if you write the email backwards, right? According to this, that's exact same representation, right? So any order in which you write the email actually has to be incorporated into the probability of this particular vector. So that's what this constant does. Turns out in practice, you never have to compute this constant ever. Can anyone tell me why? Yeah?
Because we are looking for the max.
That's right, that's right. So it doesn't actually matter, right? So if I just want to know, ultimately, I could just do the following. What is y equals spam given x divided by p of y equals not spam, or not equals spam, given x, right? So that's ultimately what I'm looking at. If it's larger than 1, then I'm going with spam. If it's less than 1, I go with not spam, right? These two have exactly the same constant, so you can just cancel the constant, okay? So you never actually ever compute this. It's just to be a little bit rigorous. All right, now I'm going to answer the burning question that you all have. What if my x's are continuous? Right, that was what you were thinking. So far, basically, we always had counts or categories. So what if we actually say my x alpha is element of r, right? Or x element of. So these are actually can be real numbers. And so here you can make many, many different assumptions. So you can basically model this with any distribution that you want. But a very common one is just the Gaussian distribution. Why the Gaussian? Because it's so nice. So basically what you're saying is, you're saying the probability that I see a certain x alpha given y is drawn from some Gaussian distribution, with mu alpha c, alpha c squared. Okay, so I basically say I take a Gaussian distribution, and it has some mean and some variance, and I have a different mean and variance for each feature and for each class. Okay, so typically, for example, if you had a classic, patient data or something, a typical one would be height, right? So height is something that's normally distributed. So here actually this Gaussian distribution is a very good, approximation. And you basically say, well, let's say I want to classify if someone is male or female. Well, in this case, actually, we have exactly this, right? We have two different means and two different standard deviations, right? And ultimately, it's a Gaussian distribution. Height is a Gaussian distribution, given that you know the gender. How do you estimate this? So just getting back to that picture. Sorry. Here we go. So if you basically have your positive points and your negative points, right? What you're basically doing is you're collapsing these onto the axis, and you say this here has to be a Gaussian distribution, right? So that's the approximation that I make. And I say this here has to be a Gaussian distribution. Then I multiply these two, and I get a Gaussian distribution here, right? Does that make sense? Raise your hand if that makes sense. Okay, awesome. So how do we estimate this? Well, for a certain feature alpha and a certain class C, what I'm saying is I sum over all. I changed my notation. Okay, well, let's just do this. So I sum over all the points that have that class C, and I just average. That's not a vector. So all I'm saying is, ignore this. This hurts your eyes. Just listen to me. What you're doing is, for each feature alpha, you just compute the average value. That's what that is. Right? You just compute the average value for within that class. So let's say take all the patient files of all men, and I compute the average height. That's mu alpha, given that they're men. Mu of height, given that they're men. And then I take all women, and I compute the average height, and that's the mu of height given female. Okay? So that's all there is to it. It's really, really simple. Where NC is the number of points in the class. So NC equals YI equals C. Any questions? So this is the maximum likelihood estimation of a Gaussian distribution. Yeah? That's exactly right. So his question is, what if I have some discrete and some continuous features, right? That's perfectly fine. You can say some I model with a Gaussian distribution. Actually, any feature could have a different model, right? That's totally fine. You just got to uphold the independence assumption, as you said. Good, so once you estimate the mean, now you estimate the variance. Well, what's the variance? This is, again, not a big deal. So, well, it's just the definition of the variance, right? So we just sum over all the data points that have that label, and I just compute the difference from the mean squared, right? That's exactly what the definition of the variance is. So hopefully that should make a lot of sense. Right? Yeah?
Do we not need to adjust for it being like a sample versus a population? Mean and standard deviation at all?
Oh, you mean put a -1 here or something? So nitpicky. I'm already assuming independence anyway. I wouldn't think it makes a difference, maybe. I'm sure someone has written a book about it. But it's a good question. It's a very good question, yes. Okay, any more questions about this? Then we're actually done with the estimation part. So just one more time. Basically, you get your data, and what you do is you assume some distribution. So you say either this is Gaussian, or this is binomial, this is multinomial, right? This has some parameters. In the Gaussian, you have the parameter mu and sigma, right? The multinomial, you have the theta, right, and so on. And then you estimate that from the data using maximum likelihood or map. And so these are basically the ways of estimating this. Please go through this and make sure you understand it. I also post a bunch of things on the homepage, pointers on the homepage, in case there's any uncertainty. Okay, one thing I want to show you. Who wants to have a demo now versus at the end? Raise your hand if you want to have it now. At the end? It's a tie. All right. Okay. All right. Oh, okay, good, good. You know I might run out of time. That's the... I guess you'd rather run out of time. Okay, so here's the, actually maybe I can show you the, well, so what you need to do for the project, maybe I first show you what you have to do for the project. So the project this time will be the following. I give you a list of baby names. So can you read this? Okay. Boys.train. So here's a list of, basically what I did is I went through some list of baby names and I randomly picked 500 names or 600 names that are boys. This, that are in the United States registered as boys. And then we also have 600 names that tend to be girls, right? So Sierra, Myra, Destiny, Annabella, etc. Right? And so the task is the following. Given a name that's not in that list, you should predict if it's a boy name or if it's a girl name. Right? And so what I want you to do in the project is to first extract features out of a name. So think about what could be good features. I give you some as an example. And so and then train a naive-based classifier, where you basically then, train a classifier with, that just takes a name and then predicts, is it a boy, is it a girl? And so I can now test this. I can demo, here we go. I don't know if you can see this. Okay. This is very small, right? This is very small. I don't know how to make it bigger. 1 second. Did I just hear someone say Viagra? 1 second. I don't know how to make it larger. Sorry. Oh, this is larger, huh? Okay, this is better? No, this is worse. Okay, this is better, right? This is better. All right, so who are you? Let's type in Stephen, right? Stephen, I'm sure you're a nice boy. Okay, so it's got it right? So then we can try Anna, right? Anna, I'm sure you're a nice girl. I know you can say Donald. Donald, I'm sure you're a nice boy. Hillary, how about Hillary? It's a nice girl. Okay, got that right. Arthur, I know you just revealed your name, so you're a nice boy. Good. You can any names you want to try? Sorry? Kilian. Oh, come on. All right. Yeah, I got it right. What if I type with double L? Oh yeah, okay, it's pretty robust. There's actually someone in the department is called Lillian. So let's see if Lillian. Ah, it's a girl. All right, perfect. What is it? Pat. P-A-T. Pat. Is it supposed to be a boy? I don't know. There's of course some that are tricky, right? So Robin. Robin could be boy or girl. Turns out it's it's a boy, but it could. Taylor, okay, Taylor. It's a boy. Alex, it could be. All right, so you see it actually works pretty well. I think it's pretty, I haven't actually, can see Timo, Nika. I know, actually, so far has gotten everything right. Anyone wants any adventurous names? Obama. Girl, here you go. All right. I'm sure Donald Trump would be very pleased to hear that he's more. Anyway. All right, so any other ones? Otherwise, can take the department chair. Let's see how that works. Fred Schneider. Okay, he's good. Okay, we are safe. All right, any last ones? Barack. Oh, I see. Barama's really a nut. Yeah, that's a boy. Okay, guys, that's actually more fair, isn't it? Trump. Here we go. Yeah, he's pretty male. All right. So this is what you have to implement as the project. And then there's going to be a competition where you basically take some test data, and then we will see who can actually get the most accurate classifier. Of course, there's an upper limit, right? Because some names can go either way. All right, let me just take a demo before we actually derive it. I can also show you a demo GNB. So this is actually, now I'm running a Gaussian naive Bayes classifier. So here's what I'm doing. I just have 2 dimensions, and I now draw some points from 2 classes, circles and crosses, and then I look at the decision boundary after training. Okay, so we first take the positive points. So I take some positive points, and then I draw some negative points, and we can now run it, and we can visualize the decision boundary. Here I'm assuming that the features are real numbered, and I assume a Gaussian distribution. So this is what we just did. And so if I now run this, this is what we get, right? So this is actually turns out, as we will prove actually this is something we will prove over in homework actually, it ends up being exactly a linear classifier, right? So implicitly, by assuming that the features are independent and that they are Gaussian, we made the assumption without realizing it that it must be a linear classifier, right? That's actually, it's relatively intuitive, because actually if you have 2 Gaussian distributions, then actually the line of where you say it's more likely to be classified from one Gaussian, drawn from one Gaussian from the other, turns out must be a hyperplane. It's relatively easy to show. So one thing you see here, it actually got all the points correct, right? So all the crosses are on one side, all the circles are on the other side. That doesn't necessarily need to be the case. So with the perceptron, we showed that it will always give us a separating hyperplane if there exists one. Turns out for the naive Bayes classifier, that's not the case. And now, can anyone come up with a data set that I could draw where that's linearly separable? The perceptron would get it right, but the naive Bayes is going to screw up. It will misclassify some points. So maybe think about it for a minute. How would I have to draw the points such that naive Bayes will not even get all the training points right? So maybe discuss it with your neighbor for a minute. Just think about it. We're trying to trick the naive Bayes classifier. Think about what it does. Yeah. All right. I think we have the first person here volunteering a data set.
What if you had one X way to the right, and then an O just to the left of it, and then a bunch of O's on the left side?
One X to the very right. Okay.
And then now we're just drawing O's. Draw one O directly to the left of that,
Yeah.
right next to it, and then a bunch of O's at the bottom.
Okay, good, 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 good. So he's basically saying, I know where you're going with this. Bam, right? It got it wrong. Why did it get it wrong? Can anyone explain it? Or can you explain it?
So because you have all those, I guess we switched the labels, but since you have all those X's on the left side, the Gaussian distribution is concentrated with the mean there. So that one outlier X over to the right isn't going to affect it.
That's exactly right. Right? So this X here is misclassified. In fact, even this X here is misclassified. Right? And what's happening is we made an assumption that these points here, if projected down here, are going to be Gaussian. Right? But actually, they're basically very heavily concentrated here. Right? And then this guy over here basically, you know, is ultimately an outlier. Right? It's so unlikely, given that you have this distribution. Right? That well, think about the other way. We're assuming this thing here is a Gaussian, right? So basically it draws a Gaussian around here, right? And it has a Gaussian for the x's over here. So this point here actually is much more likely to be drawn from the O's, right? It would make more, you know, it actually would become even clearer if we have multiple O's. So let me just draw this again. So let's say we have a bunch of O's here. And then, you know, we just have a few x's here, but the bulk of the x's really is over here, right? Then if you model this, right, it basically models these points here as a Gaussian and these O's here as a Gaussian. And clearly these points are more likely to be drawn from the O's than from the x's, right? And these 2 points just don't carry enough weight to move the mean of the Gaussian over, right? So despite that this is completely linear separable, right? A perceptron, if I had the same data set, a perceptron would actually find a classifier right here, right, in between. Does this make sense? Any questions about this? Yeah? That's right. So this is exactly, points on this line are 50-50. That's exactly right, right? So you exactly, the ratio is 1. So you could be either one or the other. Yeah? Yeah?
Which classifier is faster in terms of telling conversion?
Perceptron or knife base? Oh, knife base is much faster. Because it's just counting. So knife base, a perceptron, you keep going over the data set. Right? It's actually, it can be really slow in terms of convergence. Yeah?
So for continuous distribution, Gaussian is nicer or this works better if you don't have a idea.
So if you have a what distribution?
So like in this case, you just pick a distribution which is Gaussian. But you didn't actually give the data.
Right, right. So the problem here is that they made an assumption, and that the assumption was the data is Gaussian distributed, and that just doesn't hold, right? So that's what breaks it. So if you had a different distribution that's more accurate, then it would be better, right? So you could have a, you know, a multimodal Gaussian or something, right? Like, you know, Gaussian mixture model or something, but it gets more hairy then, right? It gets a lot trickier.
The reason Gaussian is because it's easy or because
Yeah, just because it's easy. Yeah. All right. See you all on Wednesday.